This is Introduction to Structures, Lesson 4, Bending Moments Diagrams for Simple Supported Beams. In the first place, we need to define two different situations for bending moments on a beam. The first one is called sagging moment. It's the case where the external loads produce the deformation as you see in the screen, producing compression on top of the beam and producing tension at the bottom of the beam. It is to say the fibers on top of the beam are under compressive forces and the fibers at the bottom of the beam are under tension forces. This is considered positive in our convention. The other alternative is to have a hogging moment, where the external load produces a bending in this way, producing tension on top of the beam and compression at the bottom of the beam. It is to say the fibers on top of the beam are under tension and the fibers at the bottom of the beam are under compression. So if we follow the calculation and the analysis of the simple supported beam we did before in the previous presentations, we already have calculated the reaction. So we know now that this beam is in equilibrium and is subjected to external forces equal to 10 kN per meter in the case of the UDL and 20 kN a punctual load in the middle of the beam. And these are in equilibrium with the reactions we have calculated, which are AY at the pin support equal to 32.5 kilonewtons, and the reaction that is produced in the roller, which is 17.5 kilonewtons in value. So now we know the reactions, we are able to start the calculation of the moments, the bending moments of this beam. For doing that, we're going to define a few strategic cross sections to run the calculations. So we have defined already the section A and B, the section where we have applied the beam support and the roller respectively. And we are going to define this cross section called 1 in the middle of the UDL, and this cross section called 2 under the punctual load of 20 kilonewtons. So being defining these cross sections, in the first place I want to define what exactly is the bending moment we are going to calculate for this beam, and the definition is exactly this. The bending moment at any section of an structure is equal to the summation of moments to the left or to the right of the section with the opposite sign. We are going to see in more detail what this definition means exactly, but it's important for you to remember the definition and to understand this definition. We are going to read it again. The bending moment at any section of a structure is equal to the summation of moments to the left of the section or to the right with the opposite sign. So you can run the calculation to the left of the structure or to the right of the section, sorry. So if you are calculating, for example, the moments at the section 1, you can use the left side of the structure, this side of the beam, or you can use the right side of the beam, which is all of this showing in the screen. Good. We have all the dimension, we have all the loads and the reaction on this beam. Now it's time to evaluate moments. In the first place, is we remember that at the point A and at the point B we have a pin support and a roller, and we remember that these two supports allowed rotation around a hinge in here and in here, it is to say at the point A and B. We automatically know that the moments at A and the moments at B are equal to 0 because the rotation are allowed. If the rotation are allowed, there is no possibility of producing any moments as a reaction because we are dealing here, remember, with a pin support and with a roller. If now we try to demonstrate this mathematically, we can do it because let's say we are going to evaluate the moments at the point A to be sure that this is 0 because intuitively they are 0 because the rotation are not restricted. But mathematically, if you try to write an equation to the left side of the structure at the point A, you see that at the left side of the structure there is nothing. There is no forces, there is no distances. So the summation of moment to the left of the structure is equal to 0 actually. If we do the same to the right side of the structure, basically you are going to evaluate all the moments to the right of the structure, and this is what I did in here. Because I'm doing the summation of moments to the right side of the structure, I will use the opposite sign, and this means that I will start with the minus, I will open these brackets, and I will run the operations inside these brackets. So minus bracket is open, and now the moment of this UDL in here is equal to 10 kilonewtons per meter multiplied by 3 meters, which is the equivalent loads, the equivalent punctual load of this UDL, multiplied by a distance which is from the middle of the UDL to A, which is 1.5 meters, as in here, and the moment of 10 kilonewtons per meter to the right side of the structure around the point A is positive because it's clockwise, as our convention said in here. So 10 kilonewtons per meter times 3 meters times 1.5 meters is the moment of the UDL around the point A, and it's positive. The next moment is the moment of 20 kilonewtons. 20 kilonewtons have a perpendicular distance to A equal to 3 meters. So, and because it's clockwise, it's a positive moment as well. So plus 20 kilonewtons times 3 meters is the moment of this punctual load. And minus, because the moment produced by this reaction By is anti-clockwise, 17.5 kilonewtons times 6 meters, which is the perpendicular distance from the force to the point A where we are taking the moments. I will close the bracket because there is no any other force to consider. And when I run the calculation, I realize that effectively, the moments at the point A is equal to 0. Calculated to the left or to the right, doesn't matter. The value has to be the same if we do the calculation to the left or to the right. We can do the same exercise calculating the moments at the point B. If we do it to the right with the opposite sign, there is nothing, there is no distances, there is no forces, so the moment is 0. But if we do it to the left, what we have is 32.5 kilonewtons, the reaction, multiplied by 6 meters, minus 10 kilonewtons per meter times 3 meters to calculate the equivalent loads, multiplied by 4.5 meters, the distance from the middle of the UDL to the point B, the point of reference for the moments, and minus 20 kilonewtons times 3 meters because it's an anti-clockwise moment as well. So, and all of this have to be equal to 0. And if I run the calculation effectively, this is equal to 0. So we have demonstrated mathematically that effectively the moments at the roller and at the pin support are equal to 0. Let's check now the moments to the left at the cross section 1. So we are here now, we are at the section 1. So we need to see the left side of the structure, which is all the structure in this circle I'm showing you in this screen. So the first force we have is the reaction 32.5 kilonewtons, and the distance, the perpendicular distance to the point 1, our point of reference now is 1.5 meters. The moment produced by this reaction around 1 is positive because it's clockwise. So 32.5 kilonewtons times 1.5 meters. The next force I have around 1 to the left side of the structure is this portion of the UDL. It's only half of the UDL. So it's a negative moment because we are going to have an equivalent load in here, rotating around the point 1 anti-clockwise. So the moment will be minus 10 kilonewtons per meter times 1.5 meters, the distance from A to 1, which will give us the equivalent load of this portion of the UDL, and multiply by 0.75, which is the distance from the middle of this portion from A to 1, multiplied by the distance to 1. And all of this will be the negative moment produced by the UDL, the portion of the UDL from A to 1. If I run the calculation, this value is 37.5 kilonewtons per meter. And this is the moment at the cross section 1. We can do it to the right side of the structure as well. But let's go to the second cross section and do the calculation to the left side of the structure. So we are now at the cross section 2. So the first force I have is 32.5 kilonewtons, which is the reaction at the point A, multiplied by 3 meters now because the force is here and the point 2 is here. So there are 3 meters perpendicularly to the force. This moment is clockwise, so it's positive. This is the reason why this term is positive. Minus now 10 kilonewtons per meter times 3 meters because the point 2 is in here, so we are taking the moment of the whole UDL. and multiply by 1.5 meter, because this will be the distance from the middle of this portion, the total UDL, to the point 2, which is the point of reference at this stage. And the distance 1.5 meter, of course. So this will be the negative moment produced by the UDL around the point 2. There is no any other force producing moment around 2 to the left side of the structure. So if I run the calculation, I obtain 52.5 kilonewton per meter, the moment at the cross section 2. As I said, you can do it to the right as well in both cases. So this is what I'm going to do right now. So if we were to run the calculation at the section 1 again and consider the right side of the structure, which is all this portion in here I'm showing you right now, is all the structure to the right side of the section 1. We have to start with the minus because we are running calculation to the right side of the structures. We have to use then the opposite sign. So I open the brackets, and the first thing I have producing moment around 1 is this small portion of the UDL, which is half of the UDL I'm showing you here. And this is 10 kilonewtons per meter times 1.5 meters and times 0.75 meters, which is the distance from the middle of this portion to the section 1. It's positive because it's clockwise. The second moment is 20 kilonewton times the distance from 2 to 1, which is 1.5 meter, and it's positive because it's clockwise. And finally, the moment produced by these reactions, 17.5 kilonewton times 4.5 meters, which is the distance from the force to the section 1, which is the section where we are running the calculations. Closing the brackets and doing the calculation, I found that the moment is 37.5 kilonewtons per meter, which is exactly the same we calculated when we did the calculation to the left side of the structure. And this is what has to be the case, because the moment can be calculated in to the left side of the structure or to the right side of the structure. If we do the calculation for the moments to the right side of the structure, this is the point 2. So the moment at point 2, at the cross section 2, to the right side of the structure is the moment produced to the right side, it is to say all of this in here. The only force producing moment is the reaction 17.5 kilonewtons. It's anti-clockwise, so it's negative. So if I write the equation, I start with the minus, I open the brackets. I start again with the minus because it's anti-clockwise, 17.5 kilonewton times 3 meters, the distance from the force to the point 2, which is the new reference in my calculations. Running the calculation is 52.5 kilonewton per meter, the same value we obtained before doing the calculation to the left side of the structure. So this is consistent, and this has to be the case. We cannot have two different values calculating to the left or to the side or to the right of the structure. This is a consequence of the equilibrium of the structure. So we have all the values now, and now we have all the values we need to sketch the bending moment diagram. This is what we are going to do now. So in the first place, I will sketch this line here, which will be the reference for my bending moment diagram. It's an horizontal line. Now I remember that the moments at A and B are equal to 0, so here and here the moment is equal to 0. And the moment at the point 1, at the cross section 1, is 37.5 kilonewton per meter based on my previous calculations. And this is the way I'm going to sketch this moment. I'm going to sketch this moment from the reference lines and going down because the moment is positive. This moment is positive because our convention said that positive moment and moment that produce tension at the bottom and compression at the top of the beam. And this is the case for this value. The second calculation we did was the calculation of the moments at the point 2, and the point 2 we did it to the left side of the structure and to the right side of the structure, and we found that the value is 52.5 kilonewtons per meter. And we are going to sketch in this way, the same way that before, because this moment is positive as well. And it's positive again because it's shagging bending moment that produce tension at the bottom and compression at the top of the beam. So another thing we need to know about the bending moment diagram is that under distributed load, we have a distribution as a parabolic function, and under punctual loads or in portions of the beam where there is nothing, we are going to have linear distribution of moments. And this is the reason why, in order to sketch this diagram, we will use a parabolic function from here to here, because we are under the UDL, and a linear function from here to here, connecting the moments equal to 0 at B and the moment equal to 52.5 kilonewton per meter at the point or at the cross section 2. So finally, to show a more professional bending moment diagram, this bending moment diagram gives us the distribution of the moments along the whole beam. We did the calculation only in 2 points, in 2 cross sections, and we know 2 more at A and B is equal to 0, and after we know that under UDLs the distribution is parabolic, and under the other portion is linear. So now we have this diagram and we are able to know the value of every moment at every cross section of the beam, because we just need to measure the let's say the distance from the reference lines to the function that describes the distribution of the moment, and we'll have the moments at any point or any cross section of this beam.